Okay, so we're recording the session as of now. Today's topic is, well, basically it's assignment 4. I'm going to try to give you some background information about the problem that you're trying to solve, and then I'd like to get you started a little bit on the assignment. It's a bit of a different assignment this week because you have to do some design, and you haven't done any of that yet. Mostly you've been filling in classes that you've at least partially been given. So in this one, you have to come up with a solution on your own and produce something that looks like an object-oriented solution. Right, so I'll explain all of that shortly. Okay, so the problem you're asked to solve is the Knight's Tour. So the Knight's Tour is it's a problem that involves a piece from the game of chess, and it's not always the case that every student knows what the game of chess is. So just very quickly, the game of chess is played on an 8. Well, the current version of the game is played on an 8x8 board, right? So it's just a regular. It's a regular square grid of spaces that that the pieces can move on. It's actually based on much older games from India and Persia, but the current version that is played is based on it's a European game from the 15th century. Some of you, I'm sure, will be very familiar with the game. Some of you might even be competitive chess players. For those of you that are, you know that the standard chessboard is labeled using ranks and files, right? So the numbers 1 through 8 and the letters A through H, I think. I'm not doing it that way for this assignment because not everybody understands, or not everybody is used to the standard chess notation. And secondly, it's a little inconvenient to work with the standard chess notation. So our chessboard will be labeled with just an integer coordinate, right? So the bottom left-hand square is 1, 1. The x-axis goes this way to the right. The y-axis goes up, right? So over here would be 8, 1. Up here would be 8, 8. And this would be 1, 8, right? So you can think of this as the first number as being the column, right? The second number is just the row. All right. 2. It's called the Knight's Tour because it involves the chess piece called the knight, right? And the knight's normally represented using a horse, although there are non-standard chessboards or chess games where it's a different shaped piece. Okay, the knight moves in a particular way, right? So ignoring all the other pieces that might be on the board, a knight can move. When it moves 2 squares in some direction, and then it moves 1 square in the perpendicular direction. Right? So a knight in the middle of the board can reach 8 squares, right? 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, and 2, 1. Right? If you want to, you can think of it as moving 1 square in a direction, and then 2 squares in the perpendicular direction. It doesn't matter how you think about it, right? It's the same thing either way. So that's how the knight moves. Obviously, if the knight is, say, over here, right, you can't move off the board, right? So you can't move here then to here. Right? So the pieces always have to stay on the board. And the Knight's Tour problem is, starting at some square, is there a sequence of moves where a knight can visit every square of the board while visiting each square exactly once. Right? If you've seen the assignment, then you've seen this animated GIF. Right? This GIF is generated from the assignment solution. Well, sorry, not the assignment solution. It's generated for a solution for this assignment. Right? And so you can see that it's the knight's just moving around the board. It's showing you where the knight could move in this particular tour, right? So the idea is you want to move to each square of the board exactly once. And it turns out that the Knight's Tour problem is a special case of a very important problem in computing science and in mathematics called the Hamiltonian path problem. Right? So in the Hamiltonian path problem, you're given something called a graph. So I've got this picture here, which is my very badly drawn graph. The round circles are called nodes. And the black lines are called edges, right? So edges connect nodes, right? So you can't have an edge to nowhere, right? It's a node, an edge connects a node to a node. And in the Hamiltonian path problem, you want to know, is there a path that visits every node of the graph exactly once, right? So similar to the Knight's Tour problem, right? And in this particular graph, there's lots of tours, or sorry, there's lots of paths that connect every vertex. Every node. They're also called vertices. So every node on the graph exactly once. So for example, starting here, you can go here, then here, then here, then here, here, and here, right? So you're always following edges. And there's lots of different paths on this particular graph, right? So yes, but you can have a graph where the answer is no, right? So on this graph, there's no way, the problem is over here, right? There's no way I can go from here to here. And then if I go to this node here, so if I try to visit both of these nodes, I run into the problem where I can't come back, right? So I can't do, so if I'm here, I go here, I go here, I'm not allowed to come back to that node, right? Because I've already been on this node once. So it's very easy to have a graph where there are no Hamiltonian paths, right? And it turns out the Hamiltonian path problem is itself a special case of the traveling salesperson problem. So the traveling salesperson problem is you're given a list of cities, right? So it might be to say the cities in Canada, and you know the distance between each pair of cities, right? You want to know what is the shortest path that visits every city exactly once and returns to the starting city, right? So it's called the traveling salesperson problem because it's meant to model the problem where salespeople used to travel from place to place to place, right? So it used to be the case that salespeople would travel and visit every customer, right? So there's the assumption that you have a customer in every city, and you want to know what is the path what is the shortest path, right? So what is the shortest path that the salesperson can take that will visit every city, right? And you probably want to know the shortest path because the path is related to either time or cost or something like that, right? And it turns out this is one of the most studied optimization problems in computing science, right? And it turns out variations of this problem show up in a surprising number of problem domains. And it shows up in medical informatics, so it shows up in the analysis of DNA. It shows up in a lot of manufacturing problems. It shows up in a lot of traveling problems, right? So problems where you actually are trying to travel from place to place to place, and many, 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 many other problem domains, right? Some variation of this problem shows up. It's important to computing science because, as you will learn when you take your course in complexity theory, that it's an example of what's called an NP-hard problem. Right? So you'll learn all about that probably in algorithms, I think. So CISC124 if you're in computing science, right? If you're just taking this course as an elective or something like that, then it's probably the case you're not going to end up in third year computing science course, right? But for those of you who are hoping to be in a computing science program, you will see this problem. You'll probably see this problem, and you'll get an explanation as to why it's important later on. Now, how is the Knight's Tour related to the Hamiltonian path problem? So if you draw the graph of the chessboard where the edges connect a square to another square that the knight can move to, then you get this picture here, right? So this is the bottom, this is the square in the bottom left corner, right? The knight can move from this square to that square, right? So that's why there's a line connecting these two. Similarly, the knight can start here and move to this square, right? And that's why there's an edge connecting the 2 and the 6, right? And if you just repeat this process, right? So where can the knight move from here? Well, it can move to here, right? It can move to this one. It can move over to here. It can move to here, and it can move to here, right? You end up with this. You end up with this graph, right? Where the lines are showing you connections between the squares. The numbers are just telling you how many squares this node. Oops, sorry. The 8 is telling you that there are 8 squares connected to this square, right? So 1, 2, 3, 4, 5, 6, 7, and 8, right? Obviously, in the corners, you're connected to a lot fewer squares, right? And so if you have a solution for the Hamiltonian path problem, you can just use that solution to solve the Knight's tour problem. Okay, so there's lots of variations of the Knight's tour problem. So the standard game of chess is played on a board of size 8, right? Try to solve the Knight's tour problem, or if you ask the question, how many tours are there on a chessboard of size 8, there's that many, right? So that's a very big number, right? So if you tried to solve this problem using a brute force method, right? So by brute force, I mean you try to look at every possible solution, right? So starting here, right, I'll try to find a solution by moving here, and I'll try to find a solution moving here, right? And then starting here, I'll try to find a solution by moving to here, moving to here, moving to here, moving to here, and so on and so on and so on, right? You will quickly, you will not be able to solve problems that are very large, right? So you can't even brute force the 8x8 board on a desktop computer, right? Not in any reasonable amount of time, right? You could brute force the solution for, for smaller boards, right? So for boards 5 or 6, those are feasible. 7, feasible, takes you a little while, right? 8 is more or less infeasible to solve with the brute force method. Depending on how much recursion you learned in CISC121, you may or may not be able to come up with a brute force solution on your own. So if you did recursion with some backtracking, and I don't think you probably didn't do recursion with backtracking in 121, but if you did, it's actually not hard to write the brute force solution using recursion, right? I was hoping to show that to you, but I don't think I have. I don't have time to do it, I don't think. Right. So there are also other variations of the problem. So you can study the problem on what are called irregular boards. Right? So boards that aren't square. Right. I have the web page open, I think, somewhere. Oh, this is Wolfram, which I'm sure most of you are familiar with. Right. So this is, I'm sure most of you, if you've taken calculus or linear algebra, you probably know about this website. That's a Knight's tour on this, I guess, roughly circular shaped board, right? That's a larger circular shaped board, right? And then you can do boards with holes in it, boards of funny shapes, right? There's a, it's a cloverleaf here, right? Spade there. I don't know what that is. C, Pac-Man, something like that. I don't know, right? So people study how to find these tours on irregular shaped boards as well, right? A lot less is known about tours on irregular shaped boards than on a regular board. It turns out there's quite a lot known about tours on a square board or rectangular boards. Sorry. Okay. Now. How do you solve this problem, right? So if you can't come up with the brute force solution, right, you need some other way to solve this, right? And even if you do use the brute force solution, you can't solve the 8x8 problem easily anyway. So it turns out that this problem has been studied. Well, not studied. It's been known for a long time. The first reference to the problem shows up sometime, I think, in the 1800s. Well, Warnsdorf came up with this rule in the 1800s. I think it's been studied a lot earlier than that. So Warnsdorf, came up with what's called a heuristic. Right? And again, if you are a computing science student, you're going to run into these later on in your computing science career. So a heuristic is a problem-solving technique that's usually simpler than the optimal approach, right? So normally it's some relatively simple rule or rules that tends to lead to a solution, right? So tends, doesn't always, but usually tends to lead to a solution, right? The reason you use a heuristic is because you trade optimality for speed or simplicity, right? So often using a heuristic leads to a simple algorithm or a simple solution to the problem. Doesn't always work, or it might not produce the best solution, right? It might be slower, et cetera, et cetera, et cetera, right? So there's lots of, it has, you know, it's not guaranteed to be optimal. But it tends to be simple, right? So if you look at the assignment, Warnsdorf rule is given to you in the assignment, and it's something that a CISC124 student can definitely implement, right? And it's the same solution that I showed you in the little animation, right? So the animation uses Warnsdorf rule to solve the next door problem. And there are some simple extensions that improve on the success rate. So on the 8x8 board, I think there's like 3 locations where Warnsdorf rule doesn't always work. But if you make a simple change to the rule, well, it's not a change, it's an extension to the rule. You end up being able to solve, you end up being able to get a tour starting from anywhere on an 8x8 board. Right. For small boards, Warnsdorf rule tends to work. For larger boards, it doesn't always work. Right. Okay. So in this problem, you're asked to basically solve the knight's tour problem, right? But you're asked to do it you're asked to do it by creating some classes that decompose the problem into some sensible number of classes / objects, right? So there's something called kitchen sink class or a monolithic class, right? And it's what normally happens when someone starts to learn object-oriented programming for the first time, right? So what most people tend to do when they run into an object-oriented language like Java or C++ or I guess C#, and many other languages, is that they take what they know from some previous programming language, like Python, and then they just throw everything everything that's required by the solution into a single class, right? You just toss everything into one big class, right? So that's called a monolithic class. Sometimes it's called kitchen sink class because of this expression here, right? So for the English-speaking, or I guess for the students whose first language is English, you may have heard the expression everything but the kitchen sink, right? Which basically means everything, right? So that's where the name kitchen sink class comes from, right? So if you were to do this, right, make one class to solve this problem, what would your class look like, right? So to solve the problem, you need to keep track of a few things, right? I need to know where is the knight, right? Obviously, because you're trying to figure out a tour for the knight, right? So you need to know where is the knight, right? At least where it starts anyway, right? You need at least that much. You need some way to move the knight, right? So I need some way to compute where can the knight move to next, right? And when you do that, right, you have to worry about, is the knight, does it always stay on the board, right? So you have to consider this problem here too, right? Is the move actually legal? And then you have to remember, well, I'm trying to keep track of where the knight is moving, right? Because I want to make this tour where the tour should only have each location on the board visited once, right? So you somehow need to keep track of the visited locations, right? There's more than one, so you need a collection, right? Now, when you go to do this part here, right, you now have some decisions to make, right? What collection am I going to use, right? Am I going to use an array? Am I going to use a list? Am I going to use a map? Am I going to use a set, right? You have to pick one of those, maybe more than one of those, right? And then you need to figure out, okay, so how am I going to compute the tour? Well, fortunately for this assignment, you're told you've got this handy heuristic that you can use that's not too hard to implement, right? And then you somehow need to put all of these things together, right? And so when you're learning an object-oriented language for the first time, right, this looks like a, well, depending on how good a programmer you are, or how, yeah, I guess depending on how confident you are in your programming abilities, right? This might look like a fairly difficult problem to solve, right? There's a lot of pieces that you have, well, not a lot, but there's some pieces that you have to put together and arrange them so that they form a solution, right? If you're more experienced, so if you've actually used an object-oriented programming language before, then it may be obvious, well, sorry, not obvious, then you may see a way to decompose the problem into a small number of classes that will help you solve the problem, right? Okay, so what I suggest most students do, right, where unless you have experience programming in an object-oriented language, I suggest you actually start with the kitchen sink solution, right? So just code up a solution to the problem as quickly, well, you mean not as quickly as you can, more or less, right? You should use what you learned in 121, right? So in 121, you're told you should decompose problems down into their parts, and you should represent each part of the problem with a function, or maybe functions, right? You should do the same thing here, right? So you can solve the problem by throwing everything into a big main method. You probably don't really want to do that because you have to think ahead, right? So the assignment is actually asking you, look, try to produce a solution where everything is separated into components, right? Where everything is separated into separate classes. If you throw everything into one main method, it becomes harder to separate them out into separate classes. If you put separate steps into separate methods, then it becomes a little easier to pull things apart, right? And that process of pulling things apart and reassembling them is called refactoring. Right? So refactoring is the process of restructuring an existing solution, a software solution, without changing its external behavior. Right? So once you have a solution to the Knight's Tour problem, all in one class, right? You can then take that solution apart and put them in, put the various pieces into separate classes. Right? Okay, so the reason you refactor is it improves, well, the intent is to improve the design and structure of software while preserving its functionality. So this is something that professional programmers will do, right? So they will come up with a solution. They might even release their solution, right? So they might have a product, some software product, could be a video game, right? It could be something like PowerPoint or Microsoft Word or something like that, right? And then after they've released it, they may go back to their current design and realize that there are some things that aren't great about the design, right? And they'll refactor it, right? So they might, so they'll pull apart their code and reorganize it, more or less, is what happens, right? They may even redesign entire parts. But when they put everything back together again, they end up with a similar product that they had before, right? Often when you refactor, you're trying to fix errors, right? So you're trying to debug or repair something. You're trying to repair something that's not working the way it's supposed to, right? And often the only way to do it is to refactor your code, right? So the idea for this assignment is start with the kitchen sink solution and then refactor, right? So let's do that. Well, let's do the start with the kitchen sink part anyway. I'm not going to do the whole solution for you, but I want to get you started, right? Okay, so let's quickly go back one slide here. All right, so we need to keep the following in mind, right? I need the location of the knight, right? At the very minimum, right? You have to keep track of where the knight is. So here's my tour class, right? You're told in the assignment that you should use the location class, right? It's almost the exact same class from the previous assignment, right? So in the Sokoban, question, you had this location class. It's exactly the same, except there's two new methods here, right? So you can change the X and Y location of a coordinate now, right? In Sokoban, you couldn't change the coordinate, right? Every time you needed to change a coordinate, you had to return a new object. Here, you can use the same object and just change its X and Y, right? You may not make use of that. You may not make use of that ability, but it's there if you need it. Okay, so I need to keep track of the location of the night, right? So if you were to throw everything into one class, you would probably have a field, the location of the night, right? So right, so there's your location of the night. Okay, and so I guess if you're going to start, right, if you're going to actually try to start to solve this problem, you need to have a main method, right? Public static void. Right, and either in the main method, you might make a constructor for this, you may not, right? So you could do everything with just static methods, in which case this field is more or less, it would be the equivalent of a Python global variable, right? Except it's limited in scope to the class tour. So you might just set the location here, right? So, sorry, not the private static. So if you're going to do it that way, you do it this way, right? You make it static, and then you would say night. And now you can pick a starting location, right? Whatever you want. So let's start at 1, 1. Right, later on, you might decide I want the person using the program to be able to start the night anywhere, right? And in fact, if you look at the assignment, it says you need a method that does in fact start the night somewhere, right? So, but for now, this is fine. Right? How does the night move? Okay, well, let's do that, right? So I want to know, there's lots of ways you can approach this problem, right? So you can ask for, you can write a method that moves the night to one location, right? Or returns one location where the night can move to, right? Or you could write a method that returns all of the locations that a night can move to, right? And if you stop and think about it, for this assignment, it's probably the second one that you want, right? Because you don't, you're trying to find some path over the entire board, right? And so it makes sense that if you're at some location, you're going to want to know what are all the possible squares that the night can move to, right? And so if you think about that, right, so if you reach, or if you come to that conclusion, right, you might say, well, why don't I make a method that returns all the locations that the night can move to, right? So public, it doesn't matter if you make these public, private, protected, whatever you want, not protected, but if you make them, it doesn't matter what the access modifier is on these, because you're going to pull this all apart later anyway, right? I'm going to make everything static for now. Obviously, when you decompose this into separate classes, you're not going to want everything to be static. So I want a method that returns all the locations that the night can move to, right? So a night, from any square on the board, the night can move to at least 2 other squares, which means this method has to return a collection of some kind, right? So whenever you have to return a collection of some kind, you have to decide, well, what collection do I want, right? Typically, the first collection you reach for is a list, right? Because it's the easiest to use, and it usually suffices for many problems, right? In this example, you could argue that you want a set, right? The reason you want a set is because the locations are all unique, right? The night, you don't want the night to move, you don't want to return a list, you don't want to return a collection where the same location is in the collection more than once, right? So you could argue that you could use a set, right? Turns out it doesn't matter what you use in this case. So I'm going to return a list, right? And I'm just going to call it moves, right? I know the current location of the night, so you don't need a parameter here, right? Because you can just access this field, right? The other way to do it is to have a parameter. You could do it this way. And what this method will do is returns. I'm going to return the list. Returns a list of possible moves starting from. So from is the starting location. A list. Whoa, sorry. A list of possible moves from the starting location. Okay. List is underlined in red, so you should deal with that now, right? Eclipse says it doesn't know what a list is. That's basically what it's saying. So you import, right, from Java util. Now this is underlined in red, so it's complaining that this method is supposed to return a list, but you're not returning anything. So let's return something. So let's make a list of locations. Sorry. Let's call it result. So we'll make a list object, return the result. Okay, so Eclipse is now happy about the return result, but it's not happy about array list. So again, import array list. Right, there it is up there. Okay, and now I just have to fill in this list of results. All right, so I just need to fill in the locations where the knight can move to. Right, so how do I do this? Well, the knight can move. So when the knight moves, it moves 2 squares in one direction and then 1 square in the perpendicular direction. You go back to, where's that picture? Here. You go back to this picture here, right? Or this one here, right? You can see at most the knight moves to 8 different locations, right? When it moves the, I guess there's lots of different ways to enumerate it, right? If you use the location class though, right? The location class represents a location with an X and a Y coordinate. So for the knight, you can change the X by -2, right? And then Y by ±1, right? Change the X component by -1 and then Y by ±2. Right? You change X by +1 and then Y by ±2. And you can change X by +2 and then Y by ±1. Right? So there's only 8 different locations that the knight can move to. Because there's a fixed number of locations, you might as well just enumerate those in the method. Right? So what I'm going to do is I'm going to make this array of offsets. Right? So int, I'm going to call it an offset. So the elements of the array is just a change in X and Y. Right? So I can move -2 locations to the left, and then 1 location up, right? Move -2 locations, so 2 locations to the left, and then I can go down. I can go 1 to the left, and 1 up, 1 left, 1 down, 1 to the right, 1 up. Sorry, what am I doing? 2. Right. So 1 location left, 2 up, 1 location left, 2 down, 1 right, 2 up, 1 right, 2 down, and 2 to the right, 1 up, 2 to the right, 1 down. Right. And now I just have to write a little loop. Right. I just have to loop over the offsets. So for each array, what am I going to call this? It doesn't matter. Delta. Right. So I'm going to loop over the arrays. So I have that array, then I have that array, then I have that array, then I have that array. Right. location, new location equals. Okay. So where am I starting from? Well, I'm starting from here, from X, right? How much am I changing by? Well, I'm changing by delta 0, right? So -2, -2, -1, -1, right? How about the Y location? Well, that's just from that Y. And I'm changing by delta 1. Right? So that's my next location. And then I take new lock and stick it into result. Not put, sorry, add. And voila. Right, you've got your list of locations. Now, you have to decide how are you going to, now if you stop and think about this for a second, right? Some of these locations that you're adding to the list are not valid on an 8x8 board, right? Because if my location is 1, 1, then when I subtract 2, I'm going to get -1, right? And that's not a legal board location, right? Similarly, if I'm at 8, 8, when I add 1, 2, I'm going to be at 9, 11, right? That's not a, sorry, 9, 10, and that's not a valid board location either, right? So you have to decide now, are these valid board locations or are they just some locations, right? And are you going to, so are you going to deal with is the location valid here or are you going to deal with it somewhere else, right? Let's deal with it somewhere else. You could deal with it here. Let's deal with it somewhere else. Right. So I want to know, is a location valid? Public, static, Boolean, right? True, it's valid. False, it's not. Is valid. There we go. Okay. So I want to know, is a location valid? Right? How do I know a location is valid on an 8x8 board? Well, the X coordinate of lock has to be between 1 and 8 inclusive, right? And the Y location has to be between 1 and 8 inclusive, right? So if lock X less than 1, or lock X is greater than 8, or lock Y is less than 1, or lock X, oh, sorry, lock Y is greater than 8, right? So if any of those conditions are true, I know the answer is false. Otherwise, the answer is true. That's easy, right? I'm just putting in the documentation here so that we can keep straight what these methods actually do. You're going to pull this all apart later on anyway, so these might change names and so on and so forth. But it's nice to have a little comment to say to know what exactly these methods are doing. So this returns true if a location, a specified location, is valid on an 8x8 board, right? So notice that there's an assumption happening here, right? There's an assumption that the board is 8x8, right? So if you're trying to create a more flexible solution, right? So if you're trying to formulate a solution on a different size board or a different shaped board, right? You have to rethink how you're going to implement this method, right? For an 8x8 board, this works, and false otherwise. So loc is a location. Return, well, it's going to return that. For a lot of the simpler methods that you might write, it's often the case that the description and the return type are more or less identical, right? That's not unusual. So if you find yourself writing something like that, don't worry about it. It's not unusual. Okay, so where have we gotten so far? let's go back to our little checklist here. Oop. Right, so I've got the location of the knight. I figured out how does the knight move, right? I can determine if a move is legal, right? I now need to keep track of where have I visited? What squares have I visited on the board, right? Again, there's lots of ways that you can do this, right? So there's many different possible ways that you can keep track of where you are or where you have been on the board, right? So let's, but we know that you need a collection, right? At a minimum, you need a collection of locations where you've been, right? Alternatively, you could use a collection of locations where you have not been, right? So you do it either way. But if you want to record the tour, you want the collection of locations where you've been. So you've got a few different choices at this point. Okay. So your choices are, do you use an array? Do you use a list? Do you use a set? Or you use a map? Right? So you need to make a choice here. And your decision is going to be determined by the nature of the problem that you're trying to solve. Right? So does everybody know how to use the hands up feature in Teams? Right? There's a little hand. There's a little hand symbol under, well, there's a little button at the top of your Teams, and one of the options is a hand. So raise your hand if you think you should use an array here. Anybody want the array? Okay, no one wants an array. Raise your hand if you want a list here. Good. Okay, so we have 2, 4, 6. 6 people want a list. All right. What about a map? Does anybody want a map? Okay, some people want a map. Good. Okay. And what about set? Does anybody want a set? 2 people want a set. And so, oh, 3? 3 people, 4. Good. Anybody else? 5, 6. Okay, so, and I guess roughly half of you haven't decided, right? Something like that. Are there actually comments somewhere? Where is the conversation? Here. Okay. Okay, so in this situation, so you know that the longest tour that you can have on an 8x8 board is 64, well, 63, right? 64. You want to visit all 64 squares. So your collection is not that big on an 8x8 board. So it turns out it doesn't really matter what you pick, right? You could pick a list, an array, or a set. Map is not so useful here. So you have to remember that when you pick map, right? Typically, so a map maps a key to a value, right? So a map is more or less a table with 2 columns, right? So you have to ask yourself, why am I using a map, right? So in other words, why do I need a key when all I have is a bunch of locations, right? You might be able to come up with a reason, but I can't think of an obvious one right away, right? So you probably don't want to choose a map. You could use a map, but if you think that you want a map, then you can probably get away with just a set in this case, right? The set kind of makes more sense given the context of the problem, right? So you want to make sure that your tour never includes a square more than once, right? And set will guarantee that for you, right? So you probably want a set in this case, although you don't have to use one, right? You can definitely use a list or an array, and it's not a problem.
Professor Ma.
Yes.
Could you use a map in the sense where you use the object location as the key and then store either true or false or 0 or 1 based on if it's been visited or not? Could that be done?
Yes, but you get the same, you get the exact same,
Yeah.
You get the exact same functionality if you just use a set of visited locations.
Yeah, of course.
Yeah. But yeah, there might be a reason. Actually, now that okay, so the answer is, to answer your question, it's yes, and you might want to do it that way. If you if you're trying to deal with an irregular board, you might want to do it that way, right?
Okay.
So you would define the board as a map of locations, and then true false for the value.
Yeah.
Right. So that would be one way to represent an irregular board. It's not the only way, but it's one way. You definitely do it that way for sure. So that's good. Anybody else have any questions? There are 2 hands up. I don't know if it's just because you forgot to put them down or not. If you have any questions, just unmute and ask. It's fine now. Okay. All right. So again, it doesn't matter what you use. Really, it doesn't really matter what you use. So well, let's use a set. Why not? Okay, so private static. Now, when you go to use a set, you have to decide what type of set do I want, right? And the notebook says you have a choice of 2, more or less, right? You have a hash set, you have a tree set. You can't use a tree set here because you can't sort locations, right? And a tree set is a sorted set, so you need something that's sortable. So you can't easily use a tree set, which leaves you with hash set. Depending on how you solve this problem, you might want to know the order that you're visiting the squares in, right? So it's possible to come up with a solution where you solve for the entire tour all in one shot, right? So you have some function, some method or methods that produce the entire tour, right? So you just solve for the entire tour. So you get this, you get the collection of 64 moves, right, to get the answer. If you use a hash set destroys the ordering of the elements, right? So hash set has no guarantee of the order that of the elements. There's something called a linked hash set in Java. So it looks like this. So I'm going to do this one, right? I have to import this. So okay. So a linked hash set is a hash set that remembers or that guarantees that the order that you put things into the set, that's the same order that you can the order that you iterate over elements of the set is the same as the order in which you put things in. Right. So if I put in the element 1, then element 2, then element 3, then element 4. If you use a linked hash set, when you loop over the elements, you get back element 1, then element 2, then element 3, then element 4. If you use a hash set, you might get element 4, then element 1, then element 2, then element 3, right? Or something else, right? You can get any. It makes no guarantees of the order that you iterate over. So you might want a linked hash set depending on how the rest of your solution looks like, right? So we'll just use that. And so what am I using this thing for? Right. So this is going to be a collection of locations. Right. So when I visit a square, I'm going to add it to this set. Right. Okay. So I'm starting out at this location here. Right. So I better add that location to my set because that's where I started. Right? So visited dot add. Right. When you see this, right, I make a location object here, then I make a location object here. It's the same location object, right? It doesn't matter. I don't need 2 independent locations, right? Or 2 independent. Actually, that's not true. Maybe I should do it this way. Never mind. I better do it this way just in case you do something, just in case we end up doing something funny later on. Right. So I better do it this way. So I add that location to the visited set. And now I need to figure out how do I get to the next square, right? So Warnsdorf rule tells you how to get to the next square, right? So if you read the assignment, the assignment tells you that this rule says, gives you a fairly simple way to get to the next square, right? So I'm just going to call that method next. Right. Again, you might include a parameter here. You don't need this parameter because you have the location of the knight now. Well, actually, why don't we do it this way? Let's do it this way. So this is going to return the next location in the tour from the knight's current position. Again, not uncommon that the description and the return value are the same, right? And here you're going to right. So here's where you implement Warnsdorf's rule. Given what we've already written, well, Warnsdorf rule is pretty easy to implement. You call moves. So Warnsdorf's rule, let me pull up the assignment. Here it is. Okay. So it starts at, so if you're at this location here, you're at location XY, you want to find all the unvisited locations that the knight can reach in one move, right? So I want to find all the unvisited locations that the knight can reach in one move. Well, that's not terribly hard given what I've already written, right? I've got this method moves that tells me all of the locations that the knight can possibly reach, right? So call the method. So here are your moves. Okay. So what's my from location? Well, it's the knight's current location, right? So that's just where the knight is. That was easy. Now, you have to remember not all of these moves are legal, right? So I have to check which ones are legal and which ones aren't. And similarly, oh wait, wrong, sorry. I don't want the PowerPoint, I want the assignment. I want to find all the unvisited locations that the knight can reach in one move, right? So, location in moves. I want the ones that are legal. So if lock, sorry, if is valid. Right? So if that move is valid, and right, and I haven't visited that location already, right? This thing up here is a set of all the visited locations, right? So if lock is not in the set of visited locations, right? So if what's it called? Visited names. Right. So is the move valid? Right. Is it not in the set of visited locations? Right. Go to step 2. Well, step 2 you have to check, right? So we'll have to do something here. Step 3 is a loop, right? So for each, oh, actually I'm in the loop right now. So for each visit, so for each of these valid locations, I want to count the number of unvisited locations that the knight can reach in one move from LI, right? So I'm going to leave you at this point right here, right? So I do want you to try to implement Warnsdorf. It's not very hard, to be honest, right? You're going to call moves again. So it's not that hard. And then you just go on a little bit more, right? And I haven't checked for this condition here yet either, so you'll have to do that, right? So you want to do something, oh, here. moves dot size is equal to 0. Right? Not if moves dot size equals 0. You need to figure out what are all the valid moves. So you might want to maybe remove the invalid moves here. Okay. And then get rid of this. Right. So you might want to do something like this. Right. So I'm going to yank out all the invalid moves. Right. Then check if moves dot size is 0. Maybe better yet, if moves is empty. So if it's empty, Warnsdorf rule says there's, well, basically it's saying there's no next move, right? So basically, what do I return for the location if there's no next move, right? So probably going to return null, right? And then up here, returns null if there is no next move. And yeah, and so you keep on going from there, right? Once you get all this done, right, you'll probably have to make some changes, right? You have to make some changes because the solution, sorry, the code that you're given has a class in it. Where'd it go? There, right? So it's got this tour viewer class in it, right? So you probably should go back. So what I've done so far is not going to quite work because your tour class needs to have these methods here, right? So everything I have so far is static. You have to change all of that. You have to make everything non-static. It's not hard to do, right? Once you have a working solution that satisfies this constraint, and this constraint, you can use the tour viewer class to look at the tour. Right, and you can get the animation that's shown here, where this one, right? You'll get something that looks like this, right? And then once you've got all that figured out, then it's time to start pulling the solution apart, right? You're going to want to look at the solution, and you're going to want to ask yourself, okay, so what are the meaningful abstractions that this solution is using, right? If you look at the fields, two of them are kind of obvious, right? This is more or less a board, more or less, right? That's more or less a knight, right? That combined with this, right? So that combined with that, that's more or less representing a knight and how a knight moves on a board, right? That, if you think about it for a minute, is more or less a board, right? Combined with this, right? Next, you're told has to be part of the tour class, so you need it in here, right? You have to add some other methods. And then you can start thinking about, how can I change or how can I make this work on a rectangular board, right? So suppose the board has 5 rows and 8 columns. Can I get it to work on there? The answer is yes. It's not hard to do. You can ask yourself, well, what if I want a tour for a different type of piece, right? So can I make a tour where it's not a knight, right? It's not so interesting, the other chess pieces, right? So you can have a rook's tour or a queen's tour or a king's tour, but they're not that interesting because of the way the pieces move. But it's an extension of your solution. Board. And what else is there? You might ask yourself, do I have to use the Warnsdorf rule, or can I do this some other way, right? Or can I have a solution where you can solve it with several different ways, right? And what does that look like, right? And so, yeah. So hopefully that gets you started. I think it gets you started pretty well, actually. And hopefully you'll be able to come up with an interesting, or reasonable anyway, decomposition of the problem into some more sensible classes. All right, I think I've yacked long enough. Does anybody have any questions for me?
Yeah, I have a question about Java style.
Yeah.
Is it conventional to use this when referring to any non-static variable? Like if you have a variable that's part of an instance,
Yes.
should you use this dot?
So what's the best answer for this? I guess there's two different answers for this. In CISC124, or if you're just learning the language, it's useful to use this in front of a field or a non-static method when you're inside the class, because so number one, if you it prevents you from accidentally referring to a local variable, it prevents you from accidentally referring to a local variable when you mean to refer to the field, right? So that's reason number one. Reason number two for someone just learning Java is it reinforces the idea that you're referencing a field or a method in a class instead of referring to so it reinforces the fact that the information is stored in the field, which is useful for a new programmer. When you go to work, your workplace will determine whether or not you should be using this in front of a field or not. So that'll be part of their style guidelines. Some places say that you should always use this in front of a field, and some places will say you should not use this in front of a field unless you have to. Right. So that's the long answer.
Sounds good. Thank you.
Okay. Akshaj, you asked. So far, it seems that you're just adding this into things into the same class. Well, yes, that's exactly what I'm doing. Can the actual assignment be done this way? Well, you can, but you will lose a lot of marks. So if you read the assignment says, where to go? So the assignment says it's not difficult to solve this in a single class, and you can do it in a main method, right? Where is it? Your goal, here, not your goal. Where to go? Somewhere there's a line that says, where to go? I thought I had a line in here that said it's actually part of your marks. I'm sure it's in here somewhere. But yes, it's part of your mark. So designing an object-oriented solution is actually part of your is part of the goal of the solution. Is part of the goal of this assignment. So don't throw everything into a single class unless you basically run out of time. Right, here it is up here. 40% of the assignment mark is based on your design. Any other questions? No? Okay. Thank you all for coming. I'm going to end the recording now, and I'm going